Hey everybody, we're going to talk about the logistic function. Logistic function, or logit, is the basic way that we're going to turn activities or outputs into probabilities. So the logistic function is, of course, the basic part of logistic regression. Let's take a look. So the fundamental concept behind logistic regression is this idea that, hey, if we have a data point over here that's close to the decision boundary, maybe we're not so sure what class it is, but a data point way over here that's far, far away, we're very sure what class it is. So the idea of the distance, the perpendicular distance to the decision boundary, which, hey, by the way, we know what that is. That's going to be W transpose X. So if that distance is far, then we are more certain what class it is. Okay, we have a problem, however. That distance, well, it could be any number between 0 and infinity. So how do we take an infinite potential number and turn it into a finite probability? We need some sort of squishing function that prevents things that are infinite from going above +1, or things that are negative infinite off here going below 0, because these are probabilities of a particular data point having the label positive class given X and W, right? Where we know that W transpose X is going to be our distance measure. Or equivalently, the negative of the probability that that is negative class, right? The probability that something's negative class is equal to the negative probability that it's positive class, where, of course, things are between 0 and 1. All right. So we want to make our prediction into a probability. We need some sort of function that's going to squish infinite numbers, like if x goes off to minus infinity, to make sure it's never lower than 0. And if x goes off to positive infinity, that it's never higher than 1. The main candidate for this is the so-called logit or logistic function. It has an asymptotic nature such that it never goes above 1 or below 0. Everything is always in the range of 0 to 1, like it's a probability. Okay, let's take a look at the function itself. 1 over 1 plus e to the minus x. Or, equivalently, e to the x over e to the x plus 1. Wait, how is that equivalent? Just to remind you, all you've got to do is divide by e to the x at each one of these places, and you will go back and forth between these two versions of the same function, okay? I'm showing you that because you'll see different authors using these different forms, okay? So it doesn't matter which version it is, just know that these are equivalent. So let's take a look at the simplest case of using logistic function. What if we have one variable, x, okay? And this variable x, well, if there's some threshold here where over this threshold everything is positive class, this might be a decision boundary right here, and below that threshold everything is negative class on that one variable. So the probability of class membership should go from 0 over here up to 1 over there. So we have this logistic function, this S-shaped curve. You'll also see this called a sigmoid because sigmoid means S-shaped. Okay? So this is the logistic function. E to the something over 1 plus e to the something. Well, what's the something? Linear algebra time, wx plus b. And when you have wx plus b, the idea is that at some threshold that we're going to go over, we are going to call everything over here positive class. And everything under here is going to be negative class. Typically, we take that point to be where the logistic function goes over 1/2. That is, as soon as you're over here, you're just a smidgen more likely to be positive class than chance. And when you're here at 0.48889, right, then you're just a little bit more likely to be negative class than chance. And over here, you're very sure you're a positive class, and over here, you're very sure you're a negative class. Okay? So where is this point, 0.5? Well, look at this. We label it to be positive class if wx plus b is greater than 0. You can just rearrange that if you want. We want to find the point where that b goes over to this side. So that's going to be minus b. And we have to divide through by that w, right? So it's going to be, at that point, minus b over w for a single variable. Okay? So we can also equivalently say the probability of a sample being negative class. And just to make life confusing, I've shown you the other version of this. But just know that this is exactly equivalent to e to the minus wx plus b over e to the minus wx plus b plus 1. Right? These are just divide through by this guy down here. Okay? And also, just equivalently, right, you want to take this probability that class is minus 1. Well, it's just 1 minus the probability that it's the positive class. By the way, I think earlier in the beginning of this little presentation, I said this wrong. I think I just said minus. Of course, that's not true, right? Minus a positive 1 is minus 1, and that's not a probability. What I meant to say was the inverse probability, 1 minus the probability of positive class. And you can just take that through, 1 minus e to the wx plus b over 1 plus e to the wx plus b. You can do some cancellations after factoring it out, and you get down to this version of it. Okay. So this is the main idea of the logistic regression, that we can take this guy, probability of y being positive class, we can break it out into a format that looks like this. 1 plus e to the negative wx plus b. Okay? Once we have that, we also know that the probability of negative class is going to be the inverse of that, right? It's going to be 1 minus that thing. Okay? Well, we can run that through, and it turns out that's 1 over 1 plus e. Note the difference between those is no negative sign here, negative sign here. Okay? So probability of being positive class membership is just got a negative sign here. Probability of being negative class membership has no negative sign. So here is a way to make our lives super easy. Remember, we picked y to be plus 1 and minus 1 this time. If you may remember, there have been times when we called this 0. But we don't do that here. We use minus 1 because it's a mathematical convenience. Because then we can just put y in the front there. And when y is a positive class, then y is plus 1. And minus plus 1 is, of course, a negative sign. And when y when the true value is a minus 1, then we end up with a situation where a minus leads to a plus, right? So this little version right here, it doesn't matter what class you're trying to classify. It doesn't matter if you're looking for positive class or negative class. Any old data point, it's going to be e to the minus y times wx plus b. Okay, so it's independent of y. So we can see this at work. What if we have our little example training set with some x's here and some y's, negative class, positive class, negative class, positive class, positive class. Okay? And we've got this form with the negative sign, this form without, but the generic form with minus y wx plus b covers all the bases. So our job is to find w and b to maximize the probabilities of fitting the correct label for every data point. Okay, so the probability of being, we're just going to assume that the probability of being right is going, for data point 1, is going to be statistically independent of the probability of being right for data point 2 or 3 or 4, right? Each time we're rolling the dice, we're doing it in a completely independent way. We could misclassify one data point without misclassifying the others. Well, independent probabilities are multiplicative, right? The probability of rolling 6 twice in a row on a die is 1/6 times 1/6. So the probabilities are multiplicative. We multiply each probability, because remember, these are probabilities. That's why we're doing this. We multiply each probability. By the way, that's my 7.5-year-old who's now laughing at my teaching. All right. So we multiply those probabilities together, and we want to maximize the probability of being right.
The probability of silliness.
Yeah, thanks, Ezra. Okay. So here we go. This is how we're going to do this, because we don't like products. Ezra, I have to teach this. Please go elsewhere. So we have to maximize the product here, but we don't want products. Products annoy us computationally. So it would be better if we could turn it into sums. Well, we can do that because we learned about monotonic functions earlier in the quarter. We know that the product of some monotonic function of this, like say a natural log, well, that's the same thing. It's going to have the same maximum. So we can just make this monotonic transformation and not change where our best answers are for the weights. So the natural log is right here. And it turns out, of course, that the natural log of probabilities is equal to the sum of natural logs. Now, another convenience that we can do, again, we don't have to, but it just makes our lives look nicer, is that we like to talk about loss functions as being minimizations. So we can turn the max into a min just by putting a negative sign on it, and the negative sign goes over there. So now finally, we know that our loss function is going to be to minimize this thing in here. We can make one final transformation. See that negative sign? Well, if we take that negative sign back inside the natural log, what is a multiplication out here becomes a power in here. So moving this negative sign inside the natural log just takes everything here to the -1 power. So we can arrive at our final version of the loss function. Then we took this stuff to the -1, so the denominator just becomes this thing. There's no, the denominator goes up here because it's -1 power. And so natural log 1 plus e to the -y times wx plus b. Ezra, I've got to finish this. It's another 5 minutes. Then we'll go watch the soccer game. Okay. So here we are. To solve this loss function. This is not a loss function that we can solve and get an analytic solution for. So we're going to have to do gradient descent. That means we need to know the derivative of this function. So what does that look like? Well, so we start with a natural log of something, and that's going to tell us that what we're going to have to do is do some chain rule in here, right? So the derivative of this loss function with respect to w is, this thing. So let's apply the chain rule. So the derivative of the natural log of the thing inside is going, natural log derivative is 1 over x. So we're going to have 1 over x here multiplied by the derivative of everything inside by the chain rule. Okay, next step is we need to get the derivative of this exponential. So the derivative of this exponential, the derivative of an exponential is just an exponential because exponentials are weird. They're their own derivative. So that's great. This is the derivative of the exponential that was right there. But chain rule, because exponential of the contents, so we need to do the derivative of the contents, and the derivative of the contents is going to be with respect to w. So it's going to be x times y. X times y is the derivative, this w term goes away. So here is the chain rule. Ezra, I'm not going to take you to the soccer match because you are literally interrupting my teaching. You are going to have to go to your room instead of to the soccer match.
I want to go to the soccer match.
Then please stop interrupting my teaching. This is being recorded for 200 students right now. All right, so finally, we're just going to do some factoring to make this simpler, okay? We want to break this down into less terms because this is it already. So to make it simpler, we can just take what's there and add 1 and subtract 1 to it, right? Obviously, adding 1 and subtracting 1 yields a 0, but doing that enables us to factor out the solution. So when we do that, we can, 1 over 1, hey, becomes 1. And the e minus 1, well, we can use that and make that into 1. Okay? And now we have 1 over 1 plus e to the minus y wx plus b. And over here, the minus y xi term. Okay, things are looking a little bit simpler. So the best part of all this is when you realize this is just what you started with. It's the logistic function right here. So this is really just 1 minus the logistic function. So the derivative of the logistic function is minus yx times 1 minus the logistic function. Yay! Okay. So that's it. Thank you very much for your patience, and I will talk with you in class tomorrow, and we'll try to apply